integral of x squared dx minus integral of 3 dx. So this one will give us x cubed over 3 minus 3x over 1. Then we now impute our upper and lower. So in the case where your x is 1, you have 1 cubed over 3 minus 3 into 1 over 1. That's the first case. Minus when your x is 0. So 0 cubed over 3 minus 3 into 0 over 1. So this one will give us 1 over 3 minus 3 over 1. And this one minus 0. 0 times 0 times 0 is 0. 0 over 0. 0 minus 0, 0. So this one is 0. So what's this? 3. 1 minus 3 minus 0. So which implies that 1 minus 3, that's minus 2 over 3 minus 0. And that would be minus 2 over 3. So this is the answer for the second case. Now let's talk about area under the curve. Area under the curve. Area under a curve. So under this concept, we have the formula is given. Area under the curve is integral of y dx. That's the formula for calculating the area under the curve. And the concept of this will be given two ordinates, that's two values of x. So the first thing we have to do is to integrate. We integrate what our y function is. Having integrated that, then we'll have a plus c constant because of the fact that this is indefinite integral. Then we have a plus c constant. So what we do first, the first ordinate value of x, we assume that at that point where you have the first ordinate for the value of x, the a there is 0. At point where the area is 0, you have your first value of x. Then we use those two, a0 and the first value of x, to determine our constant. Having done that, we now assume that we have a1x. So the a1x, that means at the first point where you have your x to be 1, is going to be ax1. That's at the point where your x is 1, for example. So, and if it is at the point where your x is 0, then it will be ax0. If it's at the point where your x is minus 2, it will be ax minus 2. That's how you have the trend. So what we are going to do at that point, having resolved a equals to 0 and the first ordinate value of x, where we determine our c constant, then we will now substitute the second value of the ordinate of x into the equation to determine the area under that particular curve, and that will now give us the area under that particular curve. So let's see a typical example to justify area under a curve. Find the area bounded by the curve y equals to x squared plus 3, the x axis and the ordinates x equals to 1, x equals to 3. So this is a typical example of a question that can be designed for this particular subtopic. So here you'll be given two ordinates, x equals to 1, x equals to 3. So the first thing we have to do, knowing fully well that our area A is integral of y dx. What is our y value here? Y value is x squared plus 3. So automatically we have your A to be equals to integral of x squared plus 3 dx. So we have to integrate this. If you integrate this, our A will definitely be x cubed over 3 plus 3x plus c, because of the fact that we have indefinite integral. Then now at a equals to 0, which was what I said, that's the first thing. You equate a to be 0. At that point you pick the first ordinate value of x, and that's 1. So to determine the c, that's the first objective. So here a equals to 0, then you have 1 raised to power 3 over 3 plus 3 into 1 plus c, and that will give equals to 0. 1 over 3 plus 3 plus c, which implies that our c will definitely be minus 1 over 3 minus 3, and that will be, c will be minus 3 1 over 3. This is the value of our c. And if you want to convert to an improper fraction, we have minus 10 over 3. So we go back to our equation. And definitely the equation will now be a equals to x cubed over 3 plus 3x minus 10 over 3. That will now be the equation, having calculated the value of c. Now, then we have a1x, because our x is 1. So we have a1x. So at this point, we are now to calculate when your x is now 3, the second ultimate, then you have a13. And that will be, anywhere you see your x, you place it with 3. So we have 3 raised to power 3 over 3 plus 3 into 3 minus 10 over 3. And this one will give us 27 over 3 plus 9 minus 10 over 3. So 3 here 1, 3 here 9. So that will give us 18 minus 10 over 3. If you look for the LCM of this, we are going to have 3. 3 times 18 times 3. That will be 4, 2. That's 54. That's 54 minus 10. And that will definitely give us 44 over 3 square units. That is the unit of area. So your area will definitely be 44 over 3 square units. Then if you are to determine the area under that curve, you have your y-axis, you have your x-axis. You have your y-axis, you have your x-axis, then you have, let's say this is your 0 origin, then you have a curve like this, passing through, touching this vertical axis, which is your y-axis, up this way. Then at a point here you have area, because of the fact that the maximum is 3. Let's say your 3 points is here. You have another area here. The area you are talking about. You have 1. Somewhere 1 is around somewhere here. Then you have, that will not be up to 3. So you can draw a kind of broken line here. Then this one will be your A1, which is your model. This will be the region. So you can have your A1 region this way, and you shade all this. So that means this is the area under this curve. Area on the curve, and the curve is y equals to x squared plus 3. So this is the area on the curve. Now, we have to talk about another important concept in integration, and that is integration by part. Remember that earlier we talked about integration by substitution. Now, we have to talk about integration by part, which is very, very important in integration. This subtopic is very important in integration by parts. So there is a formula for determining the integration by parts, and it is integral of u dv equals to uv minus integral of v du. This formula is very important. So this is the model where it appears. You have u dv. U will be a particular parameter that you can differentiate easily, while dv is going to be a particular parameter that you can integrate easily. U will be a parameter that the differential is known, while dv will be a parameter whose integral or integral value or integral term is known. So what am I talking about? Let's see some example to justify that. In case whereby you have your a part, let's say you have x squared ln x, x squared ln x dx Or you also have b. Let's say you have x squared ex dx. So this term is what, look at these two situations. The situation is what will definitely give us the picture of what integration by part is all about. Now, here, if you look at this, you have x squared ln x. You can integrate this easily, but this, the integral value of this is not known. In this other case too, you can integrate this easily. Integral value of this is also not known. So when you get to a situation like this, the first thing, you must not choose your u and the v wrongly. The moment you choose your u and the v wrongly, then you will not get the accurate result. So in this situation, in this a part, where I have integral of x squared ln x dx. So yeah, since I know that I can integrate this easily, then my dv will definitely be x squared. My dv here will be x squared, while my u will be ln x. So if I have to integrate dv, if I integrate dv, I will integrate x squared. And why they call it integration by part is you are integrating by part, because you integrate this, you differentiate this. And that is why it is known as integration by parts. That means you are integrating. Look at what you have, even from the formula. You are to integrate this. You leave this one, you integrate this. So it's by parts. Not that you are absolutely integrating all the parameters that you have got in the system. So in this situation now, if I integrate this, I will have v.